In the last class, we saw how we can solve a boundary value problem with Dirichlet or Robin or Neumann boundary conditions using a finite difference method. In this class, we shall consider another technique for solving boundary value problems, namely a shooting technique. What is the basic idea in this shooting technique? It converts the given boundary value problem into two initial value problems and solve the two initial value problems by the techniques which we have already studied. Namely, you can solve the initial value problems by Taylor series method or Runge-Kutta method or Euler's method or predictor corrector methods and obtain the solution of the two initial value problems. Then combine the solutions of these two initial value problems to generate the solution of the original boundary value problem. This is the basic idea behind the shooting technique for solving a boundary value problem. We shall focus our attention on 2-point boundary value problem governed by a second order ordinary differential equation with Dirichlet boundary conditions in this class. Let us see why we call this method as a shooting method. Suppose say I want to hit a stationary target at a distance which is far away from me, and I fire an artillery to hit this target. So, depending upon the angle of the barrel, the projectile will land at different locations on the target. Suppose say I start with a barrel angle which is m1 and then fire the first round and note down the location where it hits this stationary target. And I again change the barrel angle to say m2 and then fire the second round and note where the projectile lands. And now I interpolate between these two targets, and it would be possible for me to now find out that angle for the barrel at which I will be able to hit the target at the prescribed position. And so, there is an analogy between this problem and the problem that we have in hand, namely the solution of the boundary value problem by a shooting technique. What is it? We want to convert the boundary value problem into two initial value problems. And so, the barrel angle corresponds to the slope dy by dx at say x is equal to a, namely the left end point a b of the interval in which the differential equation is defined. And then hitting the target corresponds to solving the initial value problem. And finally, combining the two solutions of the initial value problem corresponds to determining the target at which I should end up, namely the solution of the boundary value problem. So, the analogy that I have explained just now is displayed here. As I said earlier, the barrel angle corresponds to the initial slope dy by dx at x is equal to a, and shooting the gun corresponds to solving the differential equation. And finally, hitting the target corresponds to matching the boundary condition where at the other end point x is equal to b, namely we want y at b to be equal to beta. So, we consider the second order boundary value problem. Y double prime x is equal to f of x. Y of 0 is 0 and y of 1 is 1. So, the differential equation is defined in the interval 0 to 1. It is a closed interval. What is our step 1? We have to transform the boundary value problem into two initial value problems. And in step 2, we should obtain the solution of these two initial value problems using any of the techniques that we have already learnt. And step 3 is combine the solutions of the two initial value problems and then generate the solution of the given boundary value problem, and we know that this is possible in the case of linear boundary value problems. And it is clear that step 1 requires the knowledge of the slope y dashed at the initial point 0. We are given y at 0 as 0, but we do not know what y dashed at 0 is. So, we have to guess this value of y dashed at 0. So, we make two such guesses and consider two initial value problems, say 1 and 2. In problem 1, we have y double prime equal to f of x, y of 0 equal to 0, which is prescribed, and y dashed of 0 is some m1 which we have guessed, because we have no knowledge of what y dashed of 0 is. That is our first problem. And what is our second problem? It is again y double dashed is equal to f of x with y of 0 equal to 0 and y dashed of 0 is m2, which is again guessed by us. And we observe that these are linear problems. So, we can apply any of the techniques that we have learnt to solve these two initial value problems. And let us denote the solution with the guess m1 by y of m11 and with the guess m2 y of m2 comma 1. So, we have two solutions y of m11 and y of m21. So, we now use linear interpolation and write down the linear Lagrange interpolation polynomial. So, what is it that I want? Corresponding to m1, my solution is y of m11. Corresponding to m2, my solution is y of m2 comma 1. What is it that I want? For some angle m3, I want, or for some angle m, I want y of m comma 1 to be equal to 1. This is the condition which is prescribed in the boundary value problem at the other end point, namely 1. So, we perform linear interpolation and write down the linear interpolating polynomial. So, we know that m is given by y minus y of m21 by the difference y of m11 minus y of m21 multiplied by m1 plus y minus y m11 by y of m21 minus y of m11 into m2. But what do we want? We want that m for which y at 1 is equal to 1. So, I substitute y of 1 here and then determine what that m is. So, we perform some simple computations and then we end up with the result that m is equal to m1 plus m2 minus m1 into y of 1 minus y of m11 divided by the difference between the two solutions of the two initial value problems that we have considered. We observe that the right hand side terms are all known to us since we have guessed m1 and m2, and we have solved the initial value problems and obtained y of m11 and y of m21. So, the terms are all known to us, and therefore, we can determine what m is, and we call this m as m3. And we now solve the initial value problem. Y double dashed is f of x with y of 0 equal to 0 and y dashed of 0 is m3 that we have computed just now using linear interpolation, and obtain the solution by any of the techniques that we know for solving initial value problem, and say the solution is denoted by y of m31. Now, use linear interpolation with m2 y of m21 and m3 y of m31 and find the new m4 and continue this process till the solution y of mk1 agrees with y of 1 that is prescribed correct to the desired degree of accuracy. So, and it is clear that the speed of convergence of this method is highly dependent on how good our initial guesses are. So, let us try to demonstrate this by the following example. So, the boundary value problem that is given to me is y double dashed equal to y of x and y of 0 equal to 0 and y of 1 is say 1.1752, and we are asked to solve this problem by shooting method. So, what is step 1? Step 1 is we must solve two initial value problems which requires the knowledge of guesses about the slope y prime at the point 0. So, we take the two initial guesses for the slope, namely y prime 0 as m1. So, let us take it to be 0.8 and m2 which is 0.9, and write down the two initial value problems. What are they? Y double dashed is y of x and y of 0 is 0 and y prime 0 is our first initial guess, which is 0.8. What is the second initial value problem? That is again y double prime equal to y of x, y of 0 equal to 0 and y prime 0 is m2 and that is 0.9, and that is what we have guessed. So, I shall use Taylor series method in solving these two initial value problems. So, what is Taylor series method? I am given an interval 0 to 1 and I have an initial value problem. Two initial conditions are given to me and I have to solve this problem using Taylor series method. So, I need to divide the interval 0 to 1 into a number of sub intervals of step size say h when I use equally spaced points, and starting with the solution which is prescribed at the initial point, I should march to the next step and then continue this process till I reach the point at which I need to get the solution, namely some point say xn which will be given to us. So, in this case let us write down the solution by Taylor series method. So, y at x is y of x minus 0 plus 0 because the initial point is 0. So, I expand y about the point x is equal to 0. So, that is y of 0 plus x into y dashed of 0 plus x square by factorial 2 y double dashed of 0 and so on plus etcetera plus x to the power of 5 by factorial 5 into fifth derivative at 0 and so on. But I know that y double prime is y, that is the given differential equation. So, I shall arrive at the values of these derivatives at 0 by making use of the given differential equation. So, y double prime is y and y of 0 is 0. So, y double prime at 0 is 0. From here I compute y triple prime. Y triple prime is y prime. So, y triple prime at 0 is y prime at 0 and y prime at 0 depending upon what my guess is I will substitute. Let us work out the derivatives which we have to compute so that we can substitute for these derivatives in this solution. So, the fourth derivative of y is y double prime, and fourth derivative at 0 is y double prime at 0, which is 0. The fifth derivative is the third derivative of y. So, the fifth derivative at 0 is third derivative at 0, but that is the first derivative at 0 and so on. So, we write down the solution y of x as, say, y of 0 is 0 plus x into y prime 0 plus x cube by 3 factorial into again y prime 0 plus x power 5 by factorial 5 into y prime 0 and so on. So, this will be y prime 0 into x plus x cubed by factorial 3 plus x to the power of 5 by factorial 5 and so on. So, it is y prime 0 into, when x is 1, 1 plus 1 by factorial 3 plus 1 by 5 factorial plus 1 by 7 factorial plus 1 by 9 factorial and so on, and that is what is given by y at 1. But what do we want? For some choice of y prime 0, we want y at 1 to be equal to 1. That is what the boundary value problem is. I do not know what y prime 0 is. That will give me y of 1 to be equal to 1, which is prescribed as the boundary condition at the other end point x is equal to 1 in the boundary value problem. And that is why we want to use a shooting technique, namely make two different guesses for this y prime 0, namely m1 which is 0.8 and m2 which is 0.9, and obtain the solution y of m11 and y of m21. So, we find using the expression above what is y at 1, that is 0.8 multiplied by these terms, and when you calculate it turns out to be this. In our notations, what we have computed is y of m11, and that turns out to be 0.9402. Similarly, with the second guess m2 as 0.9, we work out what y of 1 is, namely we are solving the second initial value problem, and that gives us 0.9 into these terms, that will give you 1.0578, and this in our notations is y of m21, and that turns out to be this. So, now that we have solutions of the two initial value problems obtained using Taylor series method, we use linear interpolation and determine the new m, which we have called as m3, and that is m1 which is 0.8 plus m2 minus m1 which is 0.9 minus 0.8 multiplied by y of 1 minus y of m11 by the difference between the two solutions. But what is y of 1? It is prescribed in the boundary value problem, and that is given by 1.1752. So, I substitute that and then do the computations, and I end up with the value of m3 to be 0.99982993. So, I have a value of m3 which is the slope y dashed of 0. So, I would now like to consider a new initial value problem. What is it? It is y double prime equal to y, y of 0 is 0 and y of 1 is this m3 which we have computed. And so, again I solve this initial value problem by Taylor series method, which gives y at 1 to be m3 times these terms. m3 is available to us. So, we substitute for m3 and compute this, and that gives us 1.1750013, and we observe that this y of 1 which has been computed to be this is close to the prescribed value, which is 1.1752. So, our initial guesses about m1 and m2 are correct, and this has led to a value of the slope, namely m3, which gives us a solution y at 1 to be very close to the prescribed value, which is 1.1752. So, having solved the initial value problem and determined the m3 which should be the slope that I should use, so that my solution will be close to the desired degree of accuracy. I write down the solution to the boundary value problem at any x in the interval 0 to 1. So, I have already divided it into a number of subintervals by means of points x naught, which is 0, x 1, which is some say 1 minus 0 by capital N, if I divide the interval into n equal subintervals. X 2 is 2 by capital N, and so on. I call these points as xi. Then the solution at any x which is xi is given by m3, which is y prime 0, which we have computed, multiplied by x plus x cube by factorial 3 plus x power 5 by factorial 5, and so on, where y at xi is given by m3 into this with x replaced by the value of xi. So that we obtain the solution, which is an approximate solution to the boundary value problem at the point xi, which is done using shooting method. Namely, we started with 2 initial value problems, solved these initial value problems by any one of the techniques that are known to us, and then we arrived at a value of the slope y prime of 0, such that that is going to give us the value of y at the end point to be as close as possible to the prescribed value, and once this is done, we determine the solution of the boundary value problem. So, this is what is the shooting technique. Let us now consider a result which gives us general conditions that ensure that the solution to a linear boundary value problem is unique. The result says, if the linear boundary value problem described by second order ordinary differential equation y double prime x is equal to p of x into y prime plus q of x into y plus r of x for x in the closed interval a b, subject to Dirichlet type of boundary conditions y of a equal to alpha and y of b is beta, satisfies the following conditions, namely p of x and q of x and r of x are continuous functions on the closed interval a b, and that q of x is greater than 0 on the interval a b, then the problem has a unique solution. So, when we work out the solution of the boundary value problem using a shooting technique, before carrying out the computations, we try to ensure that the conditions of this theorem are satisfied for that particular problem. That would ensure that the solution that we obtain is a unique solution. So, our goal is to get an approximation to this unique solution, because we are trying to solve the problem numerically. How do we do this? We know that every solution to a linear non-homogeneous differential equation can be written as a particular solution plus constant times a solution to the corresponding homogeneous problem. Therefore, we work with 2 initial problems. What are the 2 initial problems? The first problem is such that it is governed by the differential equation, which is the same as the differential equation, which is a non-homogeneous differential equation given in the boundary value problem. Then what are the initial conditions for this initial value problem? They are y of a equal to alpha. This is one of the conditions prescribed in the boundary value problem at the end point x is equal to a, and we take y prime at a to be some prescribed value. It can be arbitrarily prescribed, and we determine the solution of this initial value problem and call that as y1 of x. Then we consider the second initial value problem, and the second initial value problem is governed by the corresponding homogeneous second order differential equation which is given in the boundary value problem along with the initial conditions. What are they? Y at A is 0 and an arbitrary non-zero value is prescribed for y dash of A, and determine the solution of this second initial value problem. Call this solution as y2 of x. Then consider a combination of these two solutions of the two linear initial value problems, namely y1 of x plus k times y2 of x. What is this constant k? In order that this combination is a solution of the boundary value problem, I must have this constant k to be such that the boundary condition at x is equal to b must be satisfied. So, we try to impose this condition and find what k is, and finally, we obtain the solution of the boundary value problem. So, this is the procedure that we would like to adopt to obtain the solution of the given boundary value problem, and this technique is what is referred to as the shooting technique. So, let us see whatever that we have described here in the next few slides. So, what is my first initial value problem? The first initial value problem is such that it is governed by the second order differential equation, which is a non-homogeneous second order differential equation that is given in the linear boundary value problem, which we have been asked to solve. What should be the initial conditions that I should take? Y of A is equal to alpha. So, this is essentially the condition that is prescribed at the left end point A in the linear boundary value problem. What is y dash of A? This I prescribe. I can prescribe it arbitrarily. So, I prescribe it to be such that y dash of A is 0. So, this is my first initial value problem. I hope it is clear to you. Let us write down the second initial value problem. What is the governing second order equation in this case? It says take the differential equation to be the corresponding homogeneous differential equation for the boundary value problem. What do you mean by that? You have to put r of x to be 0. That will give you the corresponding homogeneous differential equation given in the boundary value problem. So, I consider my second initial value problem to be y double dashed equal to p of x y prime plus q of x into y. So, I have put r of x to be 0 and it is defined in the interval a b. So, what should be my initial conditions in this case? We have already described. Take y at the point A to be 0 and you can prescribe y dashed at A to be any non-zero value. So, let us take y dashed at A to be equal to 1. I hope you have understood what the two initial value problems are. Now, the existence and the uniqueness theorem for initial value problems ensures that under the hypothesis of the theorem that we had stated in the beginning, problems 1 and 2, which are initial value problems, have a unique solution. So, we move on to determining this unique solution. Suppose we denote them by y1 of x and y2 of x. Then take a linear combination of these two solutions, namely y of x is equal to y1 of x plus beta minus y1 at b by y2 at b into y2 of x. So, you may ask me how suddenly you have written down a constant in this form, namely beta minus y1 of b by y2 of b. Please recall that we had written the solution in the form y1 of x plus k times y2 of x, and we said that we determine k in such a way that the prescribed boundary condition at the other end point, namely b, is satisfied. What is the other end point condition? Y at b must be equal to beta. So, we have imposed that condition and we have arrived at the constant as this. So, I have given the explanation here. So, let us look into how we have arrived at the constant k as what is written there. So, we have taken y of x to be y1 of x plus k y2 of x. So, we compute y dashed of x, y double dashed of x, and so substitute for this y1 double dashed of x and y2 double dashed of x. What is y1 double dashed of x, which can be obtained from the first initial value problem? So, y1 double dashed of x is p of x y1 prime plus q of x y1 plus r of x, and y2 double dashed of x is p of x y2 dashed of x plus q of x into y2, because that corresponds to the homogeneous differential equation for the boundary value problem. So, we write down the coefficient of p of x, which is y1 prime plus k y2 prime, plus coefficient of q of x, which is y1 plus k y2 plus this r of x. But what is y1 prime plus k y2 prime? You observe that it is y prime, and y1 double prime plus k y2 double prime is y double prime. So, we substitute for y1 prime plus k y2 prime as y prime and y1 plus k y2 as y. So, we get y double prime of x is equal to p of x into y prime x plus q of x into y of x plus r of x. What is this? This is the second order linear differential equation that governs the boundary value problem. So, what is it that we have shown? We have shown that y of x given by y1 of x plus k times y2 of x is a solution of the non-homogeneous differential equation which governs the boundary value problem. That is what we have shown. Now, let us see about the conditions. What do we want? We want y at a to be equal to alpha, which is prescribed. Let us check what happens here. What is y at a? Y at a is y1 of a plus k times y2 of a. How have we chosen y1 of a? That is alpha. What is y2 of a? We have chosen it to be 0. So, it is alpha plus k times 0. So, it is equal to alpha. So, our y satisfies one of the conditions at the end point x is equal to a, namely y of a is alpha. What about y dashed of a? It is y1 dashed of a plus k times y2 dashed of a. But y1 dashed of a has been taken to be 0 and y2 dashed of a is prescribed to be 1, and therefore, it gives you what k is. So, our y of x, which is y1 plus k y2, satisfies the governing non-homogeneous differential equation for the boundary value problem, along with the condition that y of a is alpha and y dashed of a is k. So, we have a new initial value problem. But what do I want? I want the solution of this initial value problem such that when I compute y at b, it should give me beta, which is the prescribed value in the boundary value problem. So, I impose that condition, namely y at b is y1 at b plus k times y2 at b. But what do I want? I want it to be beta. So, this immediately tells k is beta minus y1 of b by y2 of b, and it is for this reason that we have written y of x as y1 of x plus beta minus y1 of b by y2 of b into y2 of x. So, we have, with that we should now be able to show that our y double dashed of x is equal to the right hand side, namely p of x into y dashed of x plus q of x into y of x plus r of x. So, instead of k, I have substituted that, and so we have been able to show that y of x satisfies the differential equation which governs the boundary value problem. In addition, what is y at a? it is y1 at A plus this multiplied by y2 at A, which is 0, and this simplifies to alpha. So, the boundary condition at the end point, namely the left end point x is equal to A, is satisfied. Now, what about the boundary condition at the right end point? Y at B is y1 of B plus this multiplied by y2 of B, and that gives you beta. So, our y of x satisfies the governing differential equation for the boundary value problem along with the conditions which are Dirichlet boundary conditions, and according to the conditions of the theorem, if p of x and q of x satisfy the conditions specified in the theorem, the solution that we obtain is a unique solution of the linear boundary value problem. And one thing that you must note here is that we must have y2 at B to be different from 0. Then in that case, if the conditions in the theorem are satisfied for p of x and q of x, then y of x is equal to y1 of x plus k into y2 of x will be a unique solution of the linear boundary value problem with Dirichlet boundary conditions y of A equal to alpha and y at B equal to beta. So, this describes the shooting technique for solving a linear boundary value problem with Dirichlet boundary conditions. We shall try to demonstrate this method by considering some examples, and we will continue with that in the next class.